Hello. Reviewing for abstract algebra final exam. It's only been a couple weeks since the last exam, so we haven't really covered uh, much else, but definitely wanted to make a video just going over the theorems for the last chunk that we covered. So let's get started. Except I would like it to show me the term first. Okay. So what's a kernel? It's basically the set of all elements in oh, it's supposed to be it's the set of all elements in G that map to the identity in H, where G to H is a homomorphism. So let F mapping G to H be a homomorphism of groups. Then the kernel of F is the set uh all A and G where or such that f of A equals identity in H. How to find the kernel? Just write out some steps. So first we define the mapping and define the function f. So like that mapping f of g to h and saying like f of A where A is in G gives you or equals B which is in H. F of A where A is in G giving you B which is in H. And then we want to check if it's well defined, but we may not have to check if it's well defined if Dr. C just gives us the function. So if she literally gives us the f of g to h where f of a equals whatever, we don't have to check well defined this because technically, like, she already did it by giving us the function. And then since kernel happens when it's a homomorphism of groups, you want to make sure that that F we defined is a homomorphism, and then we make our set for the kernel. Theorem 816. Let F of G to H be a homomorphism with kernel. Then the kernel is a normal subgroup of G, meaning that every kernel is a normal subgroup. Did I Oh, okay. And I forgot to say that the kernel of a homomorphism measures how far F is from being injective. So, and this theorem, 816, just basically tells us that every kernel is a normal subgroup of G. This next theorem, theorem 818, it's a couple of theorems after this 816, but I paired it here because it's the like backwards direction of this. This one's saying every kernel is a normal subgroup of G. This one is saying every normal subgroup of G is a kernel. So if N is a normal subgroup of G, then the map F of G to G mod N, given by F of A equals the coset NA, then that map is a surjective homomorphism with kernel equaling N. So to sum up, that means that every normal subgroup is a kernel. Theorem 817. Let F mapping G to H be a homomorphism of groups with kernel F. Then the kernel F is the set of the identity of G if and only if F is injective. I.e., the kernel of F is the cyclic set of the identity in G if and only if F is 1-to-1. Lemma 819. Let F mapping G to H be a group homomorphism with kernel of F equaling K, and we let A and B belong to G. Then F of A equals F of B if and only if KA equals KB, i.e. F of A equals F of B if and only if A times B inverse belongs to kernel. Theorem 820, or the first isomorphism theorem. Let f of g to h be a homomorphism of groups with kernel. And with kernel just means like the kernel exists, right? Because we have that group homomorphism. So kernel exists. Then the quotient group G mod kernel F is isomorphic to the image of F, where, just as a reminder, the image of F is that set of like all outputs. So, image of F is all F of G for all G and G. And the image of F is a subgroup or subset of H. I always forget. To continue here, so you're gonna have the quotient group. You're gonna have G mod kernel of F being isomorphic to the image of F, always, if you have a homomorphism. But if F is surjective, then G mod kernel of F is isomorphic to H, because when F is surjective, then the image of F will equal H. Steps to show the first isomorphism theorem, or that G mod kernel is isomorphic to the image of F. First, we define our mapping and function, and then check that that function is well defined, if applicable, like I mentioned before. Is it a homomorphism? Is F onto surjective? We define our kernel and we define our image, and then we see the second isomorphism theorem. So the second and third isomorphism theorems are all just basically branched off of the idea of the first one. So the first one is saying G mod kernel F is isomorphic to image of F. Um, this one is saying K mod H and K is isomorphic to HK mod H. But let's go through the whole thing. So we let K be a subgroup of G, and let H be a normal subgroup of G. Then we have a bunch of things. HK is a subgroup of G that contains both K and H, where HK equals the set HK such that H is in H and K is in K. We also have that H is a normal subgroup of HK. H and K is isomorphic to K, and K mod H and K is isomorphic to HK mod H. And finally, the third isomorphism theorem. We let N be a normal subgroup of K, and I think I messed that one up. Let N be a normal subgroup of K, and let K be a normal subgroup of G, such that N is a subgroup of K and K is a subgroup of G. So we see we've got that hierarchy. Then we have that K mod N is a normal subgroup of G mod N. And we also have G mod N mod K mod N is isomorphic to G mod K. And we have this hierarchy going on because normality is not transitive. But just remember that isomorphisms are transitive. It's just normality that's not. Just a couple of other things from her notes that were noteworthy, pun intended. For some F mapping G to H, if H is abelian, then the image of F is a normal subgroup of H. It's because image of F is always a subgroup of H, and we know that if H is abelian, then all of its subgroups are abelian, and that also leads to all of the subgroups being normal subgroups of the big abelian group. For some f mapping G to H, if f is on 2, then image of f equals H. So we mentioned that before, but I wanted to give it its own card as well. That's the end of that new material from notes, but I also wanted to go back through what well-definedness, homo, all that stuff meant, since I didn't write out some of these in the last deck. So well-defined. So we define our f and our mapping such that f maps G to H. For well-definedness, we let x equal y for some x, y, and g. Then we want to show that x equals y implies that f of x equals f of y. So not just even that f of x equals f of y, we want to show that that's literally because x equals y. Homomorphism, this is the one that I remember pretty well. We have our f such that f maps G to H, and we say for all x, y, and g, we want to show that f of xy equals f of x, f of y. And that additive version, f of x plus y equals f of x plus f of y. On to, we have our f such that f maps G to H, and we want to show for all a and h, there exists an x in G such that f of x equals a for all a. So for all outputs, there's at least one input that maps to it. And one-to-oneness, we have our f such that maps G to H, and we want to show f of x, when f of x equals f of y, that implies that x equals y. So not only are you wanting to show there that x equals y, you want to show that it's because f of x equals f of y. And that's it for this one. Yay!